Good morning, everybody. Today we're going to be going over complex numbers and how to graph them on, air quotes, a number line. It's not really a number line, it's a number plane, but it looks like it'll look like rectangular coordinates. It's technically a little different, but just keeping that in mind. And we're also going to be graphing these with polar coordinates. So some good stuff happening. But if you remember, a complex number is just any number that can be written as a real number plus an imaginary number or an amount of imaginary numbers, where that I is going to be the square I is the square root of -1. So some real number plus some amount of square roots of -1 is what we call a complex number. And we've conveniently used x and y because when we graph complex numbers on the complex number field or complex number plane, it looks like x and y coordinates. But really, if we, way back when, we have number lines, yeah? Remember number lines? When we start adding complexity to this, or complex numbers, so this is our real numbers, and these are our imaginary numbers. So this is the amount of i's that you have in your number. So like a 2, this would be 2 plus I, or 2 plus 1i. It looks like a coordinate, it kind of is a coordinate, but it's also just a number. It's not an ordered pair, I should say. So it kind of looks like an ordered pair, but it's not an ordered pair. It's one number, it's a complex number, and complex numbers need complex number fields, or number planes. So we have an imaginary portion, and it kind of looks like an XY graph, which means that we can use polar coordinates, or the idea of polar coordinates. We call this polar form because it's not technically a coordinate again, but r times cosine theta plus I sine theta, cosine theta being the real portion, or r times cosine theta being that real portion, and I sine theta being the imaginary portion. But we're going to see that we have similar strategies as yesterday and the day before, graphing polar coordinates, as we do when we have polar form of imaginary numbers or complex numbers. To plot these, again, act like this is the x coordinate and this is the amount of your y coordinate. So this looks like -3, 1. This would look like 2, √3. Again, not exactly the same thing, but very similar, and you could almost pretend like they're exactly the same thing and get away with it. But the only difference is you're graphing this on a complex number field versus the Cartesian rectangular graphs. But you do need to know the radius, you do need to know theta to put it into polar form. And again, polar form just kind of looks like this, which looks really similar to a ordered pair, but again, not exactly. I'm going to say, again, not exactly, probably 1,000 times today. Sorry. Okay, so we want to find r. R is equal to square root of √3. I'm going to ignore that negative. √3 squared plus 1 squared, which is 3 plus 1. R is the square root of 4, or 2. Now this angle, if we want to graph this, we can start there. If we want to graph this, -√3 is between 0 and 2, or sorry, 1 and 2, and there. So it should be right about there. This angle, our y value is basically 1/2, and this is basically -√3/2. So that means that we're going to have 5 pi over 6 be our angle. So we have all the pieces, we just need to plug it into our polar form. So z is equal to radius is 2 times cosine 5 pi over 6 and I sine 5 pi over 6. Shame on Mr. Renicky for putting a comma. That should be a plus sign. All right, so that's it. You don't have to, you actually don't get to figure out what cosine of 5 pi over 6 or I sine of 5 pi over 6 are. That would just be putting it back into rectangular form or standard form of these complex numbers. So this is just the form of a polar this is just the polar form of the complex number. There's nothing to do here. It's as simple as this. Just like we wouldn't do anything with this, except we just did stuff to this to put it into this form. So these mean exactly the same thing. They're just different forms. I'm going to move that little over. Now this one, same idea. This is going to be a little... So we want to find the radius first. R squared is equal to 2 squared plus root 3 squared. So 4 plus 3, r is equal to root 7. Okay, so we're going to save that for a second. And then we're going to take the inverse tan of x over y, air quotes x over y. So inverse tan of root 3 over 2. This is not one of our nice numbers that we're used to seeing. So when you type that in your calculator, you should get that it's about 40.9 degrees. My calculator was in degrees mode when I did this. You could do this using radians. It shouldn't matter. 40.9 just because my calculator was in that mode, and that's as thought out as I could get. So we're going to just put it into the form. Z is equal to R cosine 40.9 plus I sine 40.9. And again, these mean exactly the same thing. One is, I should say, about. This and this mean the exact same thing, just a different form. The reason we do these, though, is that we have a lot of, I'm going to air quotes, cool things that we could do with these, like finding complex roots of a problem. So this does have some uses beyond just we can do it, but at this point it kind of just feels like we're doing it because we can. But more stuff to come. Okay. So if you remember, x and y are r cosine theta, r sine theta. We kind of use that idea for the last problems. But we are going to use this to put it into rectangular form, so reversing the process a little bit. If we wanted to, we could distribute the 2. So we're just going to put this back into rectangular form, reversing the process. Cosine 30 is root 3 over 2. This would be I times 1/2, or I over 2. I'm going to leave it like this, though. Times 2. We're going to distribute the 2 now. We have root 3 plus I, which is rectangular form. Again, these mean the exact same thing. Using a calculator, basically you're going to type in 0.4 cosine 200, and then you're going to type in 0.4 sine 200, and it should come out as gross decimal. Those gross decimals are going to be negative 0.3759 for cosine, and then it's going to be negative, so I'm going to change that to a minus, negative 0.1368 I. So Z also equals that. much easier to go from this direction because we're used to evaluating these trig functions. The other ones, it feels weird to put it into a trig function and just leave it there, because then we just want to figure out that value, but again, that undoes what we just did. One of the amazing applications, just the greatest thing you'll ever see that you can do with these is multiply them. Multiplying, we actually had to do this last trimester. We had to multiply some complex numbers, and it's gross because you have to FOIL. But multiplying it in polar form is really easy, and I don't say that lightly. So this is really easy to multiply and divide in polar form. If I wanted to multiply or divide these in rectangular form, you have to FOIL. We didn't do this part, but if you have to divide it, it's gross. You don't want to do it. That being said, we can easily do this with it in polar form. So one application of this is just to be able to do multiplication and division faster. It doesn't make it faster if you have to convert it and then out. Maybe with the division, but not with the multiplication. So a little bit trite when I say that it's easier, because you wouldn't naturally do this with the multiplication at least. But z times w, you take the two things you're multiplying, you're going to take their radii and multiply those, and then you're also going to add the angles together. So z times w is equal to 3 times 5 cosine, adding the angles, so 100 plus 20 is 120, plus I sine also 120. This is, you could easily figure out what that is in rectangular form, but it doesn't really make sense to do that because we don't know what these are in rectangular form. So, and you want to start with the same, or you want to end with the same form you start with, unless given other directions. But you could actually figure out what this is in rectangular form. So if you wanted to, go for it. I'm not going to because I don't have to. Something that I didn't talk about, which we're going to need in a second, so I don't want to throw it on you before we start, but the standard form of polar angles, or standard of polar form is that the angle is between 0 and 2 pi. Shocker. But we are going to need that in this next one, so I wanted to bring that up before I just threw it upon you. So for z divided by w, we're going to take z, and we're going to divide the radii, so 3/5, 3 divided by 5, and then cosine angle 20 minus the other angle, and plus I sine angle minus other. So normally this would be 3/5 cosine of negative 80 plus I sine negative 80. Now we need it to be between 0 and 2 pi, or 0 and 360, so we need to add 360 to both of these, and we should get that it is cosine of 280 and then I sine of 280. You could figure out what that is in rectangular form, but again, this one would make even less sense because it's gross up here. This is gross. This one you might want to, just because 120 is not too bad. But that is all for this one. Again, just practicing switching between the forms, and one of its many uses to have it in polar form. Polar form can be nice with operations, just because we have some shortcuts for the operations, like the ones I just showed you. If you're interested, you could look up proofs on this, but we are going to be using this next week to find some more advanced roots. So exciting stuff happening. but I will see you next time.